So section R1 is what we'll start with, and it's about sets. And so if I'm moving too fast, let me know. Wave your hands, scream at me, whatever you got to do from there. Just let me know that I'm moving a little too fast or something like that. Yeah, shoot a flare or something. I don't know. But let me know what I need to do, and we'll try to get you through this. So let's just start with talking about sets. And first thing we want to do is define what is a set. A set is a collection of objects. In our case, we're going to be talking about a collection of numbers, various collections of numbers. And inside of a set, so things inside the set are called elements. Elements. That's pieces inside a set. So if I say something is an element of a set, that means it's inside the set. And the notation that I'll use for saying something is an element of a set is this Greek letter epsilon. It just looks like a C with a little line in the middle of it, is what that is. And that just means it's an element of it. That's all that means. Nothing fancy about that. It's just the notation that you'll see used on the exams and in the labs and things. So I want to try to be as consistent with that. When you're writing a set, you want to use set braces, and those look like that. So it's just curly braces is what I usually call them in my high school classes. Use the curly braces, kids. It's not square brackets, it's curly braces, that sort of thing. Because square brackets mean something totally different later on. So curly braces is what I call that. So an example of that, of a set, might be, a set of numbers, 1, 2, 5, and 7. That's a set. And we might name that set set A. And we just say A equals this set. And what we could do is we could say, okay, well, 2 is an element of A. So that's how that reads. 2 is an element of A. That's how you would say that, or that's how it could be written out in long form. So the notation is that Greek letter epsilon there, 2 epsilon A. That means 2 is part of that set A, is all that really means. Now, if you wanted to say, okay, 3, is 3 in that set? Oh, it's not there. So you could say 3 is not an element of A by just taking it and putting a slash through the epsilon. So that tells us that 3 is not an element of A. Just a lot of notation stuff that you're going to see today to get you going with this. It will be beneficial. Usually notation is not the favorite thing in the world, but it is beneficial. Okay. All right. So epsilon means it's an element of. Epsilon with a slash through it, not an element of. And then if we're going to write a set, we need to use the curly braces, the set braces, what they call it. Okay. All right. There's a few different two different types of sets that we're going to deal with. One is called a finite set. And if something is finite, it has a limited number of elements. Think about, you can count how many are in there. Our example, set A, is a finite set because there's 4 pieces in it. No more, no less. There's 4 pieces in set A. It's finite. Well, the opposite of finite would be infinite. And an infinite set is unending, unlimited, number of elements. Okay. An example of an infinite set would be the natural numbers. The natural numbers is the numbers you learned first when you were a kid. You're learning to count. You started with 1, 2, 3, 4, and you kept going forever. As you got older, you counted higher. So natural numbers would be an infinite set. It's just the counting numbers is all the natural numbers are. So this would be an example of an infinite set. All right. Let's look at some sets and decide, is the set finite or infinite? And we'll just call this example A, and I'm going to write a set, and we're going to decide, is it finite or infinite? 1, 1/2, 1/4, 1/8. Keep going. Is that finite or infinite? Infinite. That ... at the end of it, that really tells you it's infinite. That's really all that you really have to look for that. It's not finite, it's infinite. Example B, let's say we had a set 7, 8, 9, ... comma 15. So the 7, 8, 9 kind of establishes the pattern that we're going by. The ... is in the middle here, not at the end. So is that a finite or infinite set? Finite, yeah, that's exactly the case. It's finite because it stops. And it's just the counting numbers from 7 to 15 is what that is. Now, another way that they could write a set is with this notation, that they have something set up where you have X and then a straight up and down bar, and then they put this inequality in there. And they might have from 1 is less than or equal to X is less than or equal to 13. Something like that. Okay. Now, what that says is it says this set contains X's that are between 1 and 13. But it includes 1 and 13. Okay. So it has a beginning point and an ending point. So would this be a finite or infinite set? Finite, because it has a beginning and an ending point. Remember the definition for infinite is unending, unlimited sort of thing there. So you want that helps out of that. And you could list those numbers that would be in between 1 and 13. You 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 13. You could do that. So we can tell if something is finite or infinite. Okay, so that's one of the skills that we need here. One of the other skills would be listing those elements in a set. So let's list the elements in each set. And they're not as nice to us here. They don't write out the set as a list of elements. They describe what they're going to be. So this example, they've got this set. They call it X. They're just saying it's a variable, and it's that X is a natural number less than 7. Okay. X is a natural number less than 7. Remember, the natural numbers are just the numbers we learned to count on. Nothing more than that. So if we're looking for the natural numbers that are less than 7, does that include 7? No. If it's less than 7, it can't include 7. So when we write the actual list of the numbers in that set, we're looking at, well, what numbers are less than 7? Well, 1 is a natural number, 2, 3, 4, 5, 6, and we stop there because 7 is not included. So the natural numbers, again, remember, are just the numbers we count with, not the decimals in between. So there we have the list of the elements in that set. They're describing it. We list the elements of that. It's one of the skills that we'll need for this particular section. Let's do another one of those. X is a natural number. Spell natural right. Greater than 7 and less than 14. A couple of lines there to do that. X is a natural number greater than 7 and less than 14. So let's list the elements that would be in that set. So what's the natural number that's greater than 7? The next one, 8. And we're going to go up to what number? 13. Good. And we've listed the elements in that set. Not very difficult there. All right. Now let's get into a little bit more what we call set theory, and so we're going to get some definitions of some things and what they're talking about here. One of the things that they talk about is what's called a universal set. What that means is everything that is part of the discussion. So a universal set, if we're talking about the natural numbers as the universal set, that means all of the counting numbers from 1 to infinity. The natural numbers is an infinite set. The universal set, if we're talking about natural numbers, then that's the universal set. If we're talking about one large set and then some things called subsets, then the largest set is the universal set. So universal set just means everything that's part of the discussion. It's part of the things that are going on. We see some examples. You'll understand what I mean here. There's another thing called the null set, which is kind of the opposite of the universal set. The null set is an empty set. And if it's empty, it means it has no elements. The notation for that is just an empty set of brackets or a circle with a slash through it. So either of those, an empty set of brackets or a circle with a slash through it, means the null set, or no elements involved. That's what that notation you're going to use there. One more little piece of definition stuff here is a subset. Okay, a subset. It's a smaller set, like sub. It's smaller. A smaller set or group of elements. From a larger set. And that larger set oftentimes is the universal set, but it doesn't necessarily have to be the universal set out of that. Okay? So we're going to use some of that stuff here and learn some notation for that as we go here. F. Here's a couple of sets. Set A is 1, 2, 3, 4, 5, 6, 7, and 8. Numbers 1 through 8. Natural numbers 1 through 8. That's set A. Set B, numbers 2, 5, and 7. Okay. The question we want to answer is B a subset of A? To be a subset, you have to contain elements that are in the larger set. The elements in subset in B are 2, 5, and 7. Are 2, 5, and 7 in A? All three of them are. If there was one piece in B that was not in A, then it couldn't be a subset. But since all three pieces that are in B are in A, then the answer to that is yes. The notation that goes with that is this. B is a subset of A. Okay, so it's like a C with a line under it. That means subset. So that's how you would read this. B is a subset of A. Okay. We're going to use the same set A again in the next example. Set A, still the numbers 1 through 8. And I'm going to call this set D. And we'll do 10, 15, and 6. Is D a subset of A? Well, is everything that's in D and A? No, 10 and 15 are not. So the answer to that would be no. The notation that you could use for that would be D. You would write it like it is a subset and then just put a slash through it. D is not a subset of A. That's what that says. One bit of information that is kind of a theory thing that it really doesn't, it comes up every now and then, but not very often, is that the empty set is not a subset of any set. So you can't have the empty set being a subset of anything. So the empty set is just the empty set. It kind of sits on its own. It's not a subset of anything else. Okay? It's just nothing is what the empty set is. It's nothing. So that's why it can't be a subset. All right. Now, sets, so far we've been looking at them in set notation. Another way that they can be represented in this class is a Venn diagram. I don't know how familiar you are with Venn diagrams. It's the circles with the overlapping in the middle, that sort of thing. And you would have two sets. You'd have set A and B. And maybe set A has 3, 5, 7, 9. And then set B has 6, 8, 10, 14, and then the overlap are the sets 11 and 13, or the subset 11, 13. Now, what that indicates is an intersection in those two sets. Set A, if we listed all the elements in set A, it'd be everybody that's in the circle A. So that's 3, 5, 7, 9, 11, and 13 are also in that circle. They're in the football shape in the middle, but they're also in that circle. Set B is 6, 8, 10, 11, 13, 14. Curly braces did not do well that time. Okay. Now, that middle part is called the intersection. So A, and then here's how you note an intersection. It's an upside down U. That intersection is 11 and 13, the two that are in the middle of that Venn diagram. Okay. What overlap do they have? That's what the intersection means. Overlap is all that it means. Okay. Intersection is the overlap. It's the pieces that are in more than one set. Okay, that's an intersection. The more inclusive thing is called a union. The union of two sets is the complete list of all elements in both sets. Okay. The intersection is where they overlap, the pieces that are in both sets. The union is the combination of the two sets together. So A union B. So it just makes it's a U. It makes more sense than an intersection does because it's just a U for union. That makes sense. So intersection is flip over the U. It's the opposite of that. So for these two sets, A and B, the union is listing out all of the elements there. So you would have 3, 5, 6, 7, 8, 9, 10, 11, 13, 14. That's the union. It's just the combination of both sets. That's what a union is. The way that you can help you maybe decide on union and intersection. If it's a union, it's in A or B. If it's an intersection, in A and B. So or more inclusive than and is. Or is going to have more pieces. A union is going to have more pieces than an intersection. And I guess the example that I usually use is like the intersection of a road. Here in Parsons, there's a four-way stop before you get into town. And that intersection is of Highway 100 and what's the one that goes the other way? Is that 28? Is that right? But anyway, the intersection is just where those two roads cross. That's a small piece of road. Where a union is the combination of both roads all together, and that's a whole lot of highway out of that. Okay, so intersections are smaller than unions are. That should help you along the way. The intersections and unions are smaller. Okay, so let's look at a few sets and then build intersections and unions of those sets based on that. All right. What letter are we on? H. All right, so here's two sets. Set W is 9, 15, 25, and 36. And I'm just kind of randomly picking some numbers, and I'm going to make these sets do what I want them to do. And set X we'll call 15, 20, 25, 30, and 35. So the first part of this, let's find this. So I'm just going to use the notation, and we've got to decide what that means. What does that notation ask us to find? Yeah, where W and X intersect. So what numbers are in both sets? 25 is one of them. There's one more. 15. We have 15 and 25 in that intersection. So that's listing the elements of the intersection. Okay. Maybe the easier but longer question is the union of those two. And technically you don't have to put them in numerical order. I do because I just, can't stand not to. But you don't have to put them in numerical order. That's not a requirement. But most of the time you're going to see them that way. When you look in your textbook or on the quizzes or exams online, you're going to see them in order. So the union of that just joins all of the elements together. So we have 9, 15, 20, 25, 30, 35, and 36. So the union, easier problem, a little longer answer out of that, but nothing major. Okay. Let's look at these couple of small sets here. Set G that's 1, 3, 5, and set H 2, 4, 6. And let's find G intersect H. It doesn't. So the answer would be nothing. And in sets, what set is nothing? Yeah, the 0 with the line through it. Or if you wrote just an empty set of braces, that would also be okay. The empty set is the intersection of those two because there's nothing that's in both of them. So that's kind of one of the exceptional things that happens, and you just got to know what to do with it. So that's a handy thing. All right. Okay, hadn't done a definition in the last few minutes, so I guess we need to do one. The complement of a set. And this is not complement, I like your shirt, your hair looks nice. It's complement with an E instead of an I. So much different definition, mathematical complement. All right, a mathematical complement in geometry class, if you remember this from high school geometry, there was a thing called a complement, and it was the part that you needed to make an angle add up to be 90 degrees. So if you had a 30-degree angle, you needed 60 more to be 90 degrees. So 60 was the complement. It's the leftover part, okay? The complement of a set, when you're dealing with set notations, is the elements that do not belong to a set. Normally from a universal set. That's given. Okay, so maybe that's where you're going to, semicolon there instead of a comma. Normally, they're going to be found in the universal set that's given to you. The complement of the set is going to be found there. Okay, so let's look at an example that has a universal set and then a couple of other sets. Okay. All right. Set A, 1, 2, 3, 4, 5, 6, 7. Very simple. The numbers 1 through 7. Okay, that's set A. Set B, 1, 3, 5, 7. And set C, 3, 4, 6. Okay. Now, of those three sets, which one do you think is the universal set? And why? It's got more in it, right? The universal set is going to be the largest set. Okay, so if you're given 3, most of the time they're going to tell you which one's the universal set. There's a few times that they don't. And what you've just got to know is a universal set is much bigger than everything else. So the biggest set that we have there is set A, and it's larger. So that's what I'm going to, that's the universal set. So a lot of times when I have to decide that, I'll go up here and I'll note this is the universal. There's an S in there. So universal set is set A. So that helps me when I go to do subsets or complements. Definitely helps me when I do complements. Okay. So I'm going to answer a few questions. This is going to kind of tie everything back together for this section. And we're going to talk about what's going on here. So the first question I want to answer is B a subset of A? Is B a subset of A? So yes, no there. Yes. Everything that's in set B is in set A, so it's a subset. Is C a subset of A? Yes. All right, now here's where we get into the complement. What we did this whole definition before out of that. B and then an apostrophe. Basically, it's a prime mark is what they call it in math, but it's like an apostrophe, a single quote. That means the complement of B. All right. So the complement of B means everything that's in the universal set that's not in B. So looks like set B is the odd numbers, 1, 3, 5, 7. So the complement of B would be the even numbers, 2, 4, 6. All right, so the complement is, you look at, like I said, it says the complement of B. So B has the numbers 1, 3, 5, and 7 in it. We look at the universal set, we say, okay, the universal set, 1, 3, 5, and 7 are in there. It's a subset. That's important to know. And then, okay, the complement means things that are not in set B, but are in their universal. So everything that's not a 1, 3, 5, or 7. So that's where that's coming from. Okay. All right. So let's try that with set C, the complement of C. Okay. Well, the elements of C are 3, 4, and 6. So when I go to the universal set, I want everything that's not a 3, 4, or 6. That's 1, 2, 5, and 7, right? Yeah, mark those out, and that's what's left. And there's the complement of set C. The complements are really easy. A lot of set notation, a lot of notation stuff in this first little section that we're going over here, talking about sets. but it definitely, it's not extremely strenuous mathematical work. There's not a lot of calculations or anything like that. Okay. All right. So that's section R1, talking about sets. All right. So let me get another page here. We're gonna go ahead and move on to R2, and we'll get into actually a little bit more math in this section than we did in that first section for sure. R2. We're going to deal with real numbers. Real, as in R-E-A-L. Real numbers and their properties. All right. Now, when we're talking about real numbers are a particular type, numbers that we're going to be dealing with most of the time in this math class, but we actually do deal with the complex number system in here as well. So I like to explain this using boxes, and the real number systems and the complex number system tie in together. So what I'm going to do is I'm going to draw a really big box, and I'm going to call that the complex numbers. Complex numbers is the biggest box we have. Okay. The complex numbers has the imaginary numbers in there, like where you take the square root of a negative number. Those are where those come from. Inside of that box is another pretty good sized box. That's the real number box. And that's where we're going to live for a little while in this class. First few weeks, we're gonna be in the real number box. I'm going to have the complex numbers going on until, we will next week. We'll get into the complex numbers next week. So this first week, everything's going to be real numbers. Inside of the real numbers box, there's all these different kinds of numbers. Real numbers just means it's a number that we know exists. Complex numbers, those are the numbers that have a negative in the square root. Those are a little different. So that's like, I, square root of -1, 2i, -3i, stuff like that. That's in the complex number box. In the real number box, there's really nothing that just sits in the real number box, but there's a box inside of it that's almost the same. It's a really big box in there. It covers, really nothing that's outside of this box. There's irrational numbers. And then over here, I'm going to split that box in two, and then there's these irrational. Okay, rational numbers are numbers that can be written as fractions. That's what it means to be a rational number. And the way I remember that is the first 5 letters of rational is the word ratio. And in math class, normally if you're going to write a ratio, you write it as a fraction. So that's how I remember that rational numbers is talking about fractions. Okay, so rational numbers are fractions like 3/4, -7/9, that sort of thing. Those are rational numbers. Irrational numbers are numbers that cannot be written as fractions. So that's like square root of 3, square root of 2, basically any square root of a prime number, would be examples of irrational numbers, numbers that cannot be written as fractions. Rational numbers can be written as fractions. Any repeating decimal is a rational number, like 0.3 repeating is 1/3, 0.6 repeating is 2/3, that sort of thing. So rational numbers can be written as fractions. Irrational numbers cannot be. And we'll deal with those different ones as we go along here. Inside of the rational number box, there's some other boxes, okay? Inside of that rational number box, I'm drawing a blue box here. That's the integers. Integers are positive and negative whole numbers. Okay, So when we're talking about integers, we're talking about the negative numbers and then everything inside of it, of that. So there's another box inside of there. So I'm going to draw this green box that is the whole numbers. And inside of the whole numbers box, there's another box. And I should have drawn it a little bigger. I'm going to draw it a little bigger. I can't write my word in there. Is the natural numbers. All right. Now, so the natural numbers is the numbers we've already talked about. So the counting numbers, 1, 2, 3, 4, 5, and so on. Whole numbers just takes that, 1, 2, 3, keep going. Whole numbers just adds a 0 to that. Okay. So 0 added to the natural numbers makes it the whole number system. Whole numbers, if you add the negative whole numbers, like -1, -2, -3, and so on, that gets you the integers. When you add the numbers in between that, that's the rational numbers, that's the fractions, like between 0 and 1 is 1/2, so that's a rational number. What you want to think about this is, what are those Russian nesting dolls? Have you ever seen those? Where they've got, a big one on the outside and you open it up and there's a smaller one inside. That's how these boxes work. The biggest box on the outside, the complex numbers, includes the most stuff. It includes all of the boxes that are inside of it. The real number box includes all of the boxes that are inside of it. So rational numbers are part of the real numbers. Integers are part of the rational numbers, but integers are also part of the real numbers. Whole numbers are part of the integers, but they're also part of the rationals. They're part of the reals. They're part of the complex. So the further inside of these boxes you go, the more parts that you really are. So it's more descriptive. So if you're included in the natural numbers box, so you're the number 3, well, the number 3 is a natural number. It's also a whole number. It's also an integer. It's also a rational number. It's also a real number. And technically, it's a complex number. Okay, so they get these pieces. Okay, so what we're going to do here is we're going to take a set and then describe what parts of that set are natural, whole, integers, rational, and irrational. Okay, we're going to take a set of real numbers and describe that from that. So that box can kind of help us do that. All right, so this is our example, example A. Set A, and I'm just going to put a list of numbers here. -8, -6, -12/4, -3/4, 0, 3/8, 1/2, 1, square root of 2, square root of 5, 6. So that's our set that we're going to be describing the different parts of. Okay. All right. So I'm going to scroll down here. I'm going to list out what we're going to do. Okay. We're going to list the subsets of A that are natural numbers, whole numbers, integers, rational numbers, and irrational numbers. Okay, and I'm going to show you some notation that I tend to use, and you may see some in your textbook. I don't think it comes up on the quizzes and tests, but I would hate for you to get your final and there be some notation of this and you've never seen it before. There's like a capital letter that they use to note each one of these. The natural numbers, really easy to remember it. it's a capital N, but the bar in the middle is thick. It's like boldface in the middle. So that's N for natural numbers. The whole numbers, guess what? It's a big W. But they boldface that first stick down. It's like the block W, but they bold that first stick down. Integers changes. It's not I, because I is confused with the complex numbers. Integers is the letter Z. It's the weirdest thing in the world. I don't understand why. I had a math history class. We didn't address that, so I couldn't tell you why it's a Z. Maybe there's some mathematical reason for that. But it's the letter Z, and they boldface that the diagonal in the Z. And then rational numbers, I understand why they use a Q for rational numbers. And to bold that one, they put a slash in the side there. Like they just put a little diagonal off to the side. They use Q for rational numbers because Q is quotient. Rational numbers are division problems, so Q is quotient. That's why they're using a Q there. Still haven't figured out the Z for integers yet, but irrational numbers, it's just as easy. It's the Q, but then you put a slash through it, like completely through it, like that, like you would the null set. It's because that means it's not rational. Okay. So what our job is on this example is to look at that set A that I've written there, and we're going to list every number that's a natural number on there, so a counting number on there. And then we're going to look at that set and list all the whole numbers. It's okay. There should be numbers that fit into more than one category. So we're marking them into the categories they fit in. So natural numbers, that's the numbers 1, 2, 3, 4, 5, 6, that sort of thing. Natural numbers are only positive, so we don't have to look at any of these on the left side here. They're out because they're negative. Natural numbers don't include 0, so the 0's out. So I'm looking from 3/8 up. What are the natural numbers that are listed in our set?
1 and 6.
That's it, 1 and 6. Good job. Okay. The good thing about our box that we've drawn up here is if we know something is a natural number, we know it's a whole number. So the 1 and 6 better show up in the whole number set. It better show up in the integer set. They also better show up in the rational number set because they're inside of that box. So we just got to get the rest of them that go with it. So the whole numbers take the natural numbers and add what to it? All right. Got it. We're done with that one. Okay. Integers. So we know 0, 1, and 6 should be in this set. What else should be in this set? And the integers takes the whole numbers and adds the negative whole numbers to it.
-8 and -6 and 0 and 1 and 6.
All right. I think there's one more. It's cleverly disguised. Can we find it? No. Look there in between the -6 and the -3/4. -12/4 is really what? What is that if you reduce that fraction? It's 3. It's -3. So it's disguised, but it's still an integer if you simplified it. That's I threw that in there because it's kind of underhanded and a little bit sneaky, but they do that. They're going to put some numbers in there that could be simplified to make them fit into different categories. So that -12/4 is technically an integer if you reduce it. Okay, so look for those sort of things. They might even throw in like a square root of 4 in there. And we know the square root of 4 is really 2. So you've got to think, okay, can I simplify any of these? Because if I can, then that makes a difference. All right. Now, the rational numbers, we know that should include all of these integers and anything else that can be written as a fraction. So that's a pretty big set. We got -8, -6, -12 over 4. And there's a fraction right next to that. So -3 over 4 has got to be a rational number. 0 is a rational number because you could write 0 as a fraction, 0 over 1. We got 3/8. We got 1/2. 1 over 1. And then 6. So the rational number set's pretty large set in this, a pretty large subset of our set A there. Now, the irrational numbers, that's the things that are not rational numbers. Another way to write that, note that would be the complement of the rational numbers. What's the complement of the rational numbers for set A? What's the only pieces that are not in the rational numbers subset? Square root of 2 and square root of 5, yeah. And we've dissected this set A into the different types of numbers. That's one of the skills that you're gonna practice and use a little bit in the R2 section.
So when you're listing the subsets and you get to irrational numbers, it's basically just whatever's left.
Yes, absolutely. That's correct. Yeah, whatever's left. Perfect. Easy enough, right? All right. All right, so let's actually do some math now. We've done a lot of set theory here. Let's do some numbers and some calculations and things with some things. So I'm going to open up my calculator just so I can, as we go here, show you how you would use your calculator to do some of these things if you needed to. I tend to, a lot of times in my high school classes, not use the calculator very much, if at all possible. But they're asked to take state exams without a calculator. You're not. So I'm going to try to show you as much as I can to help you out as we go here. So the first thing that we're going to talk about, still in section R2, it's not a new section, is order of operations. We'll start with that because it matters in everything we do after this. I get this question every year in Algebra 1 with my freshmen in high school. They'll say, do we have to follow order of operations now? We've already finished that section, that chapter. I'm like, yes, absolutely. You have to follow order of operations for the rest of your life anytime you're doing math. If you don't follow order of operations, you're not going to get the problem right. And on Instagram and Facebook, there have been a few of these things where somebody put a thing on there. If only 20% of the population can get this right. Well, if they knew order of operations, 100% of the population could get them right. And my stepfather-in-law always misses them. He's a really smart guy, but he doesn't do order of operations correctly, and he always misses them. And he always texts me before he posts on social media the answer he got. Is this right for this problem? And it hardly ever is. So I kind of feel bad, but anyway, he learns a little something. He's getting better at it, I guess. But the first thing that you would want to look for is parentheses. That really just means any grouping symbol. So it could be parentheses, it could be brackets, like square brackets, or an absolute value sign is a grouping symbol as well. But we just use the generic term parentheses, and then exponents, multiplication, division, and then addition, and subtraction. I've always done the please excuse my dear Aunt Sally is the way I learned it. There's plenty of other little limericks that you can use, but parentheses, exponents, multiplication, division, addition, subtraction. Keep in mind that all of these should be followed left to right. Okay. We tend to emphasize that on multiplication, division, and addition, subtraction, but technically all of them should be followed left to right. So we're looking left to right through a problem and following that order of operation. We take care of all the parentheses left to right, then take care of all the exponents left to right. Multiplication and division happen together. They're not two separate operations. They actually are the same operation mathematically. You know, when you go into a whole big thing about theory, we're not going to go into. And addition and subtraction are the exact same operation. It's a whole theory thing. So when we look at that, if there's division before a multiplication and it's further to the left, you're going to do the division first. Multiplication, division should be done left to right, whatever order they're in there. Addition and subtraction, same way, left to right is how that happens. Addition does not outrank subtraction. Multiplication does not outrank the division. Keep that in. That's the most common mistake, is that we think division is lower than multiplication or subtraction is lower than addition. That's not true. They're the same level. They're the same rank as far as that goes. Now, exponents do outdo multiplication. Parentheses do outdo exponents, that sort of thing. So there's a rank to that. All right. So we talk about exponents and parentheses and all that. So I'm gonna throw some problems out here, and we're just gonna work them and do some math for a change. And I think pretty much from here on out, it's math involved in what we're doing. So we're gonna try to do that, and we'll take a break here in a little while and do some and get stretched out a little bit and go from there. So example B, we're going to evaluate. That would be the instructions that you might have here. Evaluate the expression. It just means work it out, get an answer. So the first one we're going to do is 4 to the third, and that's it. There's nothing else going on in the problem. What does it mean to say 4 raised to an exponent of 3? It means multiply 4 times itself 3 times. 4 times 4 times 4. 4 times 4 times 4 would be 64. On the calculator, so I'm using the graphing calculator here. If I wanted to use an exponent, I can do 4, and then over here underneath the clear button is the caret button, is what that's called. Looks like a little house top. You hit that, and with the newest operating system on the TIs, which if you buy one, they're going to have that. If you don't buy one, you borrow one. Depending on what version of the operating system that whoever you borrow from has, it may or may not do that. It may just show the house top symbol. It's the same thing. It doesn't matter. The newest version is more aesthetic. It looks better. It looks like an exponent. So I just put the 3 in there and hit enter, and there it is. It's 64. That's all that, I want to kind of show you where things are on the calculator, because they're not as obvious as they are on the smaller calculators, sometimes with the graphing calculator. But knowing where they're at now will help us later on. Example C, let's say we had a -6 in parentheses squared. Well, that means to take -6 times -6. A negative times a negative should turn into what kind of number? Positive. Yeah, negative times a negative is always a positive. Anybody ever watch the movie Stand and Deliver when you were in school? I tend to show that one about every year because it's about a math teacher, and there's a scene where they all say a negative times a negative is a positive, and they say it like 18 times in the scene. I'm like, they must have had trouble learning that line or something. But it's one of my favorite movies. If you have nothing else to do, watch Stand and Deliver. It's a great movie. 6 times 6, 36. Turns positive. Anytime you have a negative times a negative, it's a positive. Okay. If you want to square something in the calculator, especially when you're squaring a negative number, and the problem originally has parentheses, you want to type parentheses in your calculator because it matters. So the parentheses are above 8 and 9. So left parentheses above 8, right parentheses above 9. So I would put a -6 in there, close the parentheses, and then I can either use the caret symbol and a 2, or there's actually a button for squaring, because that's a pretty common thing to do, is square something. Over here to the left, it's highlighted in red, there's the squared button. You could use the caret with a 2. It's the same thing. And you get positive 36. If you don't put those parentheses in there, your calculator will assume that you meant to square 6 and then make it negative. So if I typed in -6 squared, it's going to give me back -36 because it does order of operations to the T. I mean, perfectly. And the way that your calculator reads this is it says, okay, square 6, because that's order of operations, exponents first, and then there's a negative out in front that I have to multiply by. Multiplication happens after exponents. So that's what it's thinking. When you put it in parentheses, it's saying, okay, this happens first, it makes it a -6, and then exponents is after parentheses, so then it squares the -6. Be very careful of that. Most common mistake for problems in this particular section and on that first exam is stuff like that, where you get the wrong sign, and then you're going to have to do something with that number after that. So be careful of that. Be very, very careful of that. I can't emphasize that enough. That you need to be careful about that. All right. Example D. Move on. Get off my soapbox. -4 to the 4th. This one does not have parentheses. So that means we're taking 4 times itself 4 times, and then we're making it negative. Well, 4 to the 3rd is 64. 64 times 4 is bigger than that. It'd be 256, I think. And negative. I'm going to use a calculator to check that because I make mistakes quite often. If you don't believe me, ask my wife. She knows. -256. That's the right answer. And again, I'm typing it in exactly like it's written. If I can type it in exactly like it's written, my calculator is going to do it right. I mean, it has no choice. Okay. All right. Example E. Let's go ahead and go to 4 times 3 squared plus 6 times 4. So a more order of operations problem. We got a lot more going on here. We got parentheses. We have an exponent. We have some multiplication. We have some addition. So we're going to follow order of operations. I'm going to do it by hand, and then we're going to type it in the calculator just to show that it can be done that way, and we get the correct answer. If we're looking at order of operations, the first thing that should happen would be parentheses. So 4 times 3, 12. And then the next step would be exponents. So we're going to square the 12, 144. And I'm doing this one step at a time. Obviously, you could do more than one step at a time. And then the next step after exponents is multiplication or division, left to right. Well, there's a multiplication there, 6 times 4, which is 24. And then the last step would be the addition. So it'd be 168, be the final answer. And I'm going to go back to the calculator, go to the original problem, and type it in and show you that your calculator really does follow these order of operations perfectly. Parentheses 4 times 3 squared, and then plus 6 times 4. 168. Exactly the same thing I got. It just followed the order of operations for me. So don't shy away from using your calculator. You may have had math teachers in the past said, "Oh, don't even use your calculator for that." I don't care. Use your calculator. It's okay. You know, not. I used to be anti-calculator for a lot of things, but yeah, you walk around with a cell phone that'll do more than the NASA computers that sent a man to space in the 60s will do. So you got a calculator on you all the time. So use the thing. It's okay. All right. Unless you're going to be an engineer, and I don't think any of you guys are engineering majors. I may be wrong. Let me know if I am. Let's do this. 6 divided by 3 plus 2 to the third times 5. What should happen first on this problem? The exponents, yeah. We don't have any parentheses here. So the exponent, 2 to the third power. So that's going to be 2 times 2 times 2, which would be 8. Then what should happen next? Division. Division and multiplication happens next, left to right. So the first one is 6 divided by 3, which is 2. And then multiplication to the right there, 8 times 5 would be 40. So that ends up being 42 as an answer. This is like one of those problems I've seen on Facebook and things where they're posting and trying to get people to answer it wrong. Kind of a gotcha kind of thing. If you go to your calculator, this one's kind of important to show you how to type that in, because if you're using the newer operating system, you've got to be careful about your exponent thing. So I'm going to do 6 divided by 3, and it'll use a fraction, a slash there instead of a division symbol, because that's common. It's a little less screen space too. Plus 2 to the third. So 2 raised to the third. And notice that my cursor is still blinking in the exponent area. I got to press the right arrow key to get out of that, to get the times. If I'd have hit times while I was up there, it'd have been multiplying the times the exponent of 3 instead of that times 5. Okay, so be careful of that. Make sure you're not still in the exponent area when you're writing your next thing. And there's 42. Get the right answer out of it. It follows order operations awesomely. It's really good. Okay. All right, let's look at next problem. 4 plus 3 squared over 6 minus 5 times 3. They like to put these in there, and they look hard, and because it's a big fraction, but it's not. Okay. One of the things with this stuff that you've got to look at it and say, okay, well, it's a big fraction. There's no parentheses in there written, but there's an implied parenthesis that you do the top part separate from the bottom part is what you want to do, and then do the division last is what you want to remember with these types of problems. So if I do the top part first, the exponent happens first, so it's 4 plus 9. And then the bottom part, the first thing that should happen would be the multiplication, 5 times 3. So that's going to be 6 minus 15. And then I would do the top part first. 4 plus 9 is 13. And 6 minus 15 would be negative 9. And we get negative 13 over 9. Now, here's where the calculator use, you've got a couple of options. One of the options is to do them as two separate problems, like the top part and the bottom part. Or I'm going to show you how I would do this if I needed to use the calculator to do that. I would put the top part in parentheses, 4 plus 3 squared. So I put that in parentheses, and then I would use the division symbol, and then I would use another set of parentheses to do the 6 minus 5 times 3 and close those parentheses. That separates it, top part divided by bottom part. If you don't use those parentheses, it will not do it correctly. Okay, and then I hit enter, and I'm getting this decimal out of that. I don't want a decimal answer. I want a fraction answer. So I'm going to hit math and then enter twice. And that'll turn any answer I get back into a fraction. So math, enter, turns decimal answers into fraction answers from there. You can set the newer calculators to where they automatically do fractions. I don't do that because there's times that I need a decimal. So I'd rather just get the answer as a decimal and turn it into a fraction, as opposed to having to turn fractions into decimals. That's, it's the same amount of keystrokes, but most of the time I'm not getting decimal answers anyway. I'm getting regular number answers out of that. So there's the negative 13 over 9. It doesn't matter whether the negative is with the 13 or with the 9 or out in the front like it is there. It's the same answer.
On these type of problems, do we always leave it as a fraction like that?
Yeah, yes, ma'am. Leave it as an improper fraction. I normally don't turn anything into a mixed number out of that. And kind of my rule of thumb usually is that if it didn't have a decimal in the original problem, the answer is not going to be a decimal either. That's my general rule out of that, is leave it as an improper fraction. If you did encounter a mixed number on the test, you can turn that into a mixed number. Just say 9 goes into 13 one time with 4 left over, so it's -1 and 4/9. But I think that the software that I use to create your test leaves them as improper fractions. I'm fairly certain on everything that you'll see, it'll be an improper fraction out of that. Good question. Good question. All right. Okay, so there's a fraction type problem. Let's look at some evaluation problems that are really the same thing, but they're going to throw some variables in there and say, okay, evaluate this when x equals -2, y equals 5, and z equals -3. And I use one of the things as we go through the course, when there's a z, I put a slash through the middle of it so it doesn't look like a 2. So if you see a slash through the middle of something in my handwriting, it's a z. If there's not a slash through it, it's a 2. Because my z's and 2's, as the day wears on, I get a little lazy and they end up looking alike. Instead of looking like z's and 2's, they look like 2's. All of them do. So, what letter are we on here? J. Let's get one. Nope, I didn't. All right. So let's say we had -4x squared minus 7y plus 4z. So we're just taking those values for x, y, and z that they gave us and plugging them in. And I plug them in every time I use parentheses when I put them in there. That will save you a ton of headaches if you will do that. Get into that habit. Whether you're using the calculator or not, if you will put them in parentheses, that'll save you some headaches, because there, if you don't use parentheses when you put the -2 in there, it could cause a sign error out of the problem. Not really affected, on the other two pieces, but for here, when we have an exponent, for sure, the parentheses matter. So then I'd work that out. So it'd be -4 times 4 minus 35 plus -12. So that's -16. And put that together. So that'd be -51 and -12. Be -63. I'm just working that out. Again, you got a calculator, put it in there. I'd straight up go -4 parentheses -2 squared minus 7 parentheses 5 plus 4 parentheses -3 -63. So it cranks out the answer. It's no shame in doing that. That's absolutely fine to do. But evaluating, when it gives you the variable value, just plug it in, work it out. Nothing, no major work to that. It's really, really simple stuff. Okay. All right. Now, in the same section, let's simplify an expression. Simplifying implies that you're not going to get a number answer. You're not going to get the answer is -63. You're going to get something, a little bit larger than that. That's maybe has variables involved. So when you're simplifying, you're putting together the like terms. Okay, so that's what we want to focus on here, is like terms. And to be a like term, that means you got to have the same letter or no letters, and you've got to have the same exponents on that letter. for that to happen. Okay, so we'll take our first example. Okay. 6 plus 9 plus x. Very simple problem. The like terms in this problem would be 6 and 9. So 6 plus 9 is 15 plus x. And you're done. You cannot combine 15 and x because they're not like terms. One is a variable, one is not a variable. Okay. It's a very simple idea. You might have 7 minus 2 plus 3x plus 6 squared plus 5x. Again, life is still ruled in the math world by order of operations. If you don't do order of operations, you're not going to do it right. You're not going to get the correct answer anyway. Okay, so not consistently. So we want to follow order of operations. So parentheses are going to come first. So I'm going to go to the parentheses that are in the problem and simplify that first. 7 minus 2 plus 3x. 7 and 2 are like terms. So that would be 5 plus 3x. And then I would go to exponents. 6 squared, 36. And then once I've done those things, then I can combine like terms with order of operations. So I've got addition with the 5 and what's its like term? 36. 5 plus 36 would be 41. And then 3x adds to get what? 8x. That's right. Anytime you're adding or subtracting variables, the exponent on the variable doesn't change. That's a pretty common mistake. The only time that you're going to change exponents on variables is if you're multiplying variable like x times x is x squared. X to the third times x squared is x to the fifth. That sort of thing. We're not multiplying variables here. We're adding, subtracting them. So be careful of that, and you'll be okay. All right. Let's throw some fractions in there because everybody loves fractions. 5/8 times 16y plus 3 times 2y. So again, we're going to follow order of operations. Can't combine anything until order of operations is taken care of. So addition and subtraction is between the two terms here, but we've got some multiplication that should happen first. So we're going to multiply 5/8 times 16. I'm not really good at fractions, so I'm not ashamed to say 5 divided by 8 times 16. You get 10. And then I can do the other one. 3 times 2, y would be 6y. Really easy to do. Now, are those like terms? Yeah, they're both y's. So put them together. 16y. That's it. Easy peasy. All right, let's do one more of those. So we had 10x times 6 over 5 minus 3x plus 13y. So what does the first piece turn into? 12x, good. 5 goes into 10 2 times. 10 times, or 2 times 6 would be 12x. And we have a minus 3x and a plus 13y. So combine the like terms. 9x plus 13y. Again, with simplifying, you're usually not going to get one, a nice little one number answer. You're going to get some other stuff there. All right. Okay. Let's do one more section before we take a nice little break for today, and then go from there. All right. So you will see some of these sections showing up more than once, like R3 is going to show up a few times in the course. And it's going to be parts of each section. R3 is like a huge section in your textbook. It has a ton of stuff in it. We're going to mainly focus on some basic things in R3 in this first section about polynomials, and it involves simplifying and stuff like that, adding, subtracting, distributive property, things like that. But then we'll go a little further in a couple of weeks. Next week we'll get into R3 again, do some other stuff with it, and then we'll pick up R3 again in week 4. So we're doing several different pieces of R3 as we go here. So the first section of R3 that we're going to talk about is talking about some rules of exponents, and we'll review rules of exponents over and over, seems like in here. Rules of exponents. The first rule of exponents is called the product rule. Product rule says add exponents. So if you had x to the 5th times x to the 3rd, you add those exponents, be x to the 8th. So product is multiplication. If you're multiplying two letter or variables or base, the variables are called the base because they're the part at the bottom. The base is the same. You add the exponents if you're multiplying. That's the product rule. The power rule is where parentheses are involved. You're going to multiply. That's what you do with the, what's underneath in parentheses is what you do with the exponents. So if we had x to the 6th with a 2 on the outside of the parentheses, this is the power rule. Anytime it's parentheses with an exponent on the outside to one or multiple things multiplied together on the inside, it's going to be multiply the exponents. So that'd be x to the 12th. We're getting some examples as we go here. And then the other exponent rule that we'll deal with here is the quotient rule. Quotient. That's division. And division is the opposite of multiplication. So if in multiplication you add exponents, in division you would have to subtract exponents. So that would be something like where you have x to the 13th over maybe x to the 5th. And you subtract those two exponents, top minus the bottom. 13 minus 5 would be x to the 8th. You deal with them that way. Okay. So what we're going to do is we're going to simplify a few exponent rule problems, and then we're going to deal with some other things with polynomials as we go here. Different ideas with section R3. And then we'll take a break and come back after a short lunch break and finish up today's material. So, from there, okay. All right. Let's do some examples. And then the instructions would be simplify. And we'll start over at A for this section. Maybe we had y to the 6th times y to the 5th. What's going on between those two pieces? Multiplying. So what are you going to do with the exponents? Add them up. So it'll be y to the 11. Very, very simple idea. If you have numbers that work their way into it, maybe you had 3x to the third times 4x to the fifth. What do you do with those numbers that are in front? Just multiply them, because that's what the problem says do. It says multiply. 3 times 4 would be 12. And then what do we do with the exponents on that? It would be x to the 8th. Very, very simple idea. Doesn't get much more difficult than that, as far as that particular rule goes. Okay. Well, let's go, examples with the power rule. We got x to the 5th to the 3rd. What's that turn into? X to the 15th. Good job. Awesome. What if there's more than one thing inside the parentheses? Take, for example, this problem. 2 to the 3rd, x to the 4th, and then that's all squared. Well, the exponent on the outside still multiplies to the exponents on the inside. So we end up with 2 to the 6th, x to the 8th. And then we're going to go ahead and work out what 2 to the 6th power is. 2 raised to the 6th, 64. So I'm going to write that number, 64, x to the 8th. 2 to the 6th power is not a huge number. It'll fit on our calculator screen, so we can do it that way. Sometimes they'll throw this at you. Where they have a fraction on the inside of the parentheses. It's no different than example D was. The exponent on the outside of the parentheses still multiplies to the exponents that are on the inside, both top and bottom. So that ends up being 3 to the 20th over n to the 12th. And I'm not sure what 3 to the 20th is. I think that's a pretty big number. We might not be able to evaluate that. We can. 348 678 4401. 348 678 4401. 34 billion. Oops, I miscalculated. Now. 33,486,784,401. Big number. Push this over into 12. Not doing anything with that number there. Be nice to have a check for that, but I don't guess we're going to. Especially not. In case you didn't know, you're not going to make that much money teaching. If you're going to be an educator. You'll make slightly less than that, but it's a good job. I love it. Let's look at zero exponent. That's another thing that we didn't talk about the rule for that, but the zero exponent's nice. It's beautiful because it's the easiest problem in the book. Because if you have something to the 0 power, no matter what it is, it could be that 3 billion 486,700 or 486,784,401. It could be that number to the 0 power. It turns into 1. No matter what is raised to the 0 power, it turns into 1. Always. You could have, x squared y to the 5th in parentheses. If it's got a 0 power on the outside, even though those are variables and you don't know what they are, what their number value is, then you can Change them into ones. It's a 1. Everything to the 0 power is a 1. Okay. All right. 0 exponent taken care of. Let's talk about polynomials now. All right. Polynomials. Terms separated by addition or subtraction. So if I talk about how many terms does the polynomial have, it's how many pieces are separated by addition or subtraction. Okay. So terms separated by addition or subtraction. Coefficients. Those are the numbers in front of variables. All right. Degree of a term. And this is something that deals with the exponents on the variables only. It's the sum of the exponents on the variables. Now, remember, that's a degree of a term. We're not combining them for all of the terms together. It's for each individual term. Then we will look at the terms degrees, the individual degrees for each term to determine the degree for the polynomial, okay? And that's a very easy, if you can get the degree of each term, the degree of the polynomial is the easiest part, okay? So we're going to look at some polynomials, and we're going to determine their degree and start with that. I think if we get that under our belt, the rest of it's going to fall in place really, really, really well. H. All right, so here's our polynomial. We want to state the degree. Oops. Spell degree correctly. State the degree. All right, so our polynomial is 2x squared plus 5xy to the third minus 6x. Okay. So how many terms does this polynomial have? 3. There's 3 pieces that are separated by addition and subtraction. So it's got 3 terms. What we want to do is find the degree of each term. Okay. So I'm going to write underneath here term degree. What's the degree of the first term? So for degree of a term, we're talking about the sum of the exponents on the variables. Well, there's only one variable for this term. What's the exponent on it? 2. So the degree of that first term is 2. But when we look at the second one, it's got 2 variables. What's the exponent on the x? 1. So the sum of the exponents on the variables for that term would be what? 4. So the degree of that term is 4. What's the degree of the last term? 1, because the exponent on the x, when there's nothing written there, is a 1. Now, that's the degree for each term. The degree for the polynomial is the biggest one. The degree is 4. So you find the degree of each term, and the degree of the polynomial is the biggest one. That's it. It really is that easy to find the degree of a polynomial. Take the biggest one. Okay, so maybe write that down. Degree of a polynomial is the highest term degree. All right, so we looked at the exponents on the variables. So 2 here, so that's the degree of that term. This one had a 1 and a 3. 1 plus 3 is 4. So that's the degree of this second term. The third term only had the x and has degree of, it has exponent of 1, so the degree of that is 1. Okay? So 2, 4, and 1 are the ones we're choosing from. To find the degree of the whole polynomial, you just pick the biggest one, 4. So that's why the degree is 4 for this polynomial. You're going to find the degree of each individual term and then pick the biggest one for the polynomial, for the whole polynomial, is what we're doing here. It's really easy when they're nice and they give you a polynomial like this one, 4x to the third minus 5x squared plus 6x to the fifth minus 7. Because when we look at the degree term, or the term degree, the first term, it only has one variable. So its degree is 3. The second one's degree is 2. Third one is 5. What's the degree of the last one? It doesn't have any variables. So if there's no variables there, it's going to be 0. So the degree of a constant is 0. That means there's no variable on it. It's going to be 0. The degree of the whole thing is what? Got all the term degrees there. So the degree of the polynomial would be the biggest one, 5. Just pick the biggest one. Do one more. Quick one here. 2x to the fourth, y to the third, minus 3x to the fifth, y, plus x to the sixth, y squared. A little bit more difficult one here because you've got to account for multiple variables, but still not a break us in two kind of problem. What's the degree of the first term? We got 4 and it'd be 7. What's the degree of the second term? 6. The degree of the last term? 8. So the degree of the whole polynomial is 8, the biggest one. And so finding the degree of a polynomial isn't terribly hard. You only look at variables. Don't worry about the coefficients in front or the constants. They're not going to matter. It's the variables that deal with that. The degree where that's going to come back in play is when we start solving polynomials. The degree can help us find how many answers we're going to have. That's where the degree, that's why we find it. It's for what we're going to do later on. Not today, but later on in the course. We solving some polynomials, okay? So there's one piece of the puzzle. Let's get to the next piece of the puzzle, which is naming polynomials. If you name a polynomial, Bill is a good name. Bobby's a great name. But that's not how we name them. We name them by the number of terms that they have. Okay, that's supposed to be a joke. Nobody gets it. The number of terms is how you're going to name a polynomial. Or you're going to really, I guess naming it is not the right way of saying it. That's what it's always been called, but it's describing the polynomial by the number of terms that it has. If it has one term, the prefix for one in English is mono, so we call it a monomial. Okay. If it's got 2 terms, the prefix for 2 would be binomial. like a bicycle has 2 tires. If it's got 3 terms, the prefix that we would use would be trinomial, like a tricycle has 3 tires. Okay. Anything bigger than that, 4 plus, we're just going to call it a polynomial. We don't go into the fact, like a quadrinomial or a quintinomial, that's hard to say, quintinomial, or anything like that. Anything 4 plus, we're just going to call it a polynomial. So monomial is 1 term, binomial is 2 terms, 3 terms is trinomial. Really, really basic thing. Where they make it a little bit more difficult is that they're going to give you this sort of problem. And they're going to say simplify and name the polynomial. So they're going to combine something we've already done with this name the polynomial game. I have no idea what letter I'm on. Okay. So they're going to say, okay, we have 2y to the 4th minus 3y squared plus y plus 4y to the 4th plus 7y squared minus 6y. So if we're going to simplify, we're going to put what together? Like terms. Okay, so we got 2y to the 4th. It goes with what term? 4y to the 4th. So when we add those together, what's it going to be? Don't change the exponent because we're adding and subtracting, so we don't change the exponent. Just change the number in front. 6y to the 4th. And then we have a negative 3y squared and a positive 7y squared. Be positive 4y squared. The 7's bigger. And then we have 1y and a negative 6y. It'd be negative 5y. So we've simplified the polynomial. How would we name that? How do we describe that polynomial? It's a, how many terms? It'd be a trinomial because it has 3 terms. Trinomial because it has 3 terms. Let's do one more, and then we'll take a break for lunch and come back, and we'll rest our brains for a little bit, and we'll come back and do the other half of our stuff for. Let's say we had 4 parentheses x squared minus 3x minus 5 parentheses 2x squared minus 8x. Okay. All right. So here's a problem that combines almost everything we've done mathematically this morning. We've got multiplication, addition, subtraction, and then combine, and then a polynomial to deal with here. So we've got order of operations to do here. So what should happen first in this problem? Very good. Distribute the 4 and the negative 5. So the 4 is going to multiply to the stuff in the parentheses it's beside. So that's going to give us 4x squared minus 12x. And then she said distribute the negative 5. That's absolutely correct. Make sure when you're distributing here that you take the sign with it. So it's a minus 5, so you're going to distribute as a negative 5. If it were a plus, you would distribute a positive. So make sure of that when you're doing your distributive property. So I'm distributing negative 5 to both of those. So that'd be negative 10x squared. Negative times negative is positive 40x. Then combine like terms. So positive 4, negative 10, negative 6x squared, negative 12, positive 40, be 28. So we've combined like terms. How would we describe that polynomial? Binomial, yeah, because it has two terms. A binomial. All right. So that gets us through the first part of R3 that we'll use in the semester. Again, I said we'll come back to R3 a couple of times after this. We've got some more stuff to cover after lunch. Let's take a. I know you guys in Jackson have a lot of options for lunch. We don't have as many here in Parsons, but traffic will be an issue. So let's take lunch till say 12:30. Would that be okay with you guys? Are y'all okay with that kind of break in the middle here?
Oh, yeah.
Yeah, are you okay with that? Okay. You guys okay with that? Take a break till that'll give you a chance to rest, splash some water on your face, wake up, that sort of thing. Let's take a break. 12:30, we'll come back and we'll pick up from there. And today will probably be the longest day of lecture of the whole summer. I promise. The rest of them get shorter. So today's a pretty heavy day because we spent about 45 minutes talking about the beginning of the course. So today is a little long, but let's take a break, go to lunch, relax for a little bit, and then we'll come back 12:30. We're going to start back. Okay?
Okay.
Yeah.
I'm the deal taking. I'm kind of irrelevant. But when you made your joke about naming that,
Yes, ma'am.